There is exactly one company on Earth that can build the machines that print the world's most advanced computer chips. It's called ASML. It sits in a small town in the Netherlands, and the entire reason it has that power comes down to a single part almost nobody can name. Then, a team of physicists, led by Tsinghua University, published a result in the journal Nature that pointed to a completely different way to make that part. A way that doesn't need ASML at all. And it's the one thing this monopoly was never built to survive. And that single part is not the machine at all. When people talk about ASML, they picture a machine the size of a bus that costs more than a commercial airliner, and that machine is real. But the machine is the easy part. The thing nobody else on Earth can reliably produce is the light it makes. Every advanced chip is printed by shining light through a stencil onto a silicon wafer, and the smaller the wavelength of that light, the smaller the features you can carve. The most advanced chips need light with a wavelength of 13.5 nanometers. That's called extreme ultraviolet, or EUV. And here's the problem. Light that short basically does not exist in any usable form in nature on Earth. You can't buy an EUV bulb. You have to manufacture the light itself from scratch, and that turns out to be one of the hardest engineering problems humanity has ever solved. Here is how ASML does it, and I want you to sit with how insane this is. Inside the light source, a generator fires molten droplets of tin, each one about 25 microns across, roughly a quarter the width of a human hair. Those droplets fall through a vacuum chamber at around 70 meters per second. As each droplet falls, a high-power laser hits it, not once, twice. The first pulse flattens the droplet into a tiny pancake. The second pulse vaporizes it into a plasma that reaches around 200,000 degrees Celsius. That's hotter than the surface of the sun by a wide margin. And in that fraction of a second, the dying tin plasma spits out a flash of 13.5 nanometer light. Then the whole thing repeats, 50,000 times, every single second. And the laser doing that is its own kind of madness. It's a carbon dioxide laser built by the German firm Trumpf, and it starts out as a beam of just a few watts. That beam gets amplified more than 10,000 times through 5 separate stages until it's carrying tens of kilowatts of average power, with peaks measured in megawatts. Also, it can smack a falling speck of tin at exactly the right instant, tens of thousands of times a second, for months on end without missing. This is the kind of thing that sounds made up. When national labs like Lawrence Livermore first started seriously researching EUV back in the 1980s, plenty of respected scientists believed it was simply impossible. It took the industry roughly 30 years and tens of billions of dollars to prove them wrong. That 30-year head start is the thing everyone else is chasing. There's also a hidden cost to doing it this way. Firing 50,000 tin explosions a second inside a sealed chamber is a filthy process. Tin vapor and debris coat everything, so the chamber has to be flooded with hydrogen gas to sweep the mess away. The collector mirror slowly degrades anyway, and the whole machine needs constant, expensive maintenance just to keep the light clean. Every hour a light source spends being serviced is an hour a machine worth hundreds of millions of dollars isn't printing anything. Hold on to that detail, because it becomes important later. That laser-produced plasma light source is the beating heart of every EUV machine on the planet, and it is the real reason ASML has no competition. The Dutch company doesn't even build all of it alone. The lasers come from Trumpf. The mirrors, some of the flattest, most perfect surfaces ever manufactured, come from another German company, Zeiss. The plasma source technology traces back to a California company called Cymer, which ASML bought outright. What ASML actually owns is the ability to make all of these impossible pieces work together, tens of thousands of times a second, for thousands of hours without failing. Decades of accumulated knowledge, locked inside one company, protected by patents and gated by export controls. And this is where you have to understand just how much power that gives them. ASML is the sole manufacturer of EUV lithography machines, the only one on the planet. There is no second supplier anywhere in the world. A standard EUV machine already costs upward of $200 million, and the newest generation, the high-NA machines with bigger optics, run around $380 million each, roughly double. That's for one tool. To manufacture a single leading-edge chip, whether it's the processor in your phone or the AI accelerators training the models everyone's talking about, the pattern has to be printed by an ASML machine. There is no other door. That position pushed ASML's market value past $670 billion, a European record. When CNBC asked Chief Executive Christophe Fouquet what was stopping the company from charging even more, he essentially conceded they hold all the cards. And one analyst, Daniel Newman of the Futurum Group, put it bluntly, this company has the market completely cornered. So that's the board. One company, one impossible light source, an entire world of technology bottlenecked through a factory in the Netherlands. And that is exactly why the Nature paper mattered so much, because the whole American and Dutch strategy for slowing China down rests on one assumption. The assumption is that this light source is so hard to build that no one can recreate it in secret, and no one can go around it. Block the machine, and you block the chips. That was the entire theory of the case. Now, over the past couple of years, you've probably seen headlines and videos claiming that China secretly built its own EUV machine, that it cloned ASML, that the monopoly is already broken. And most of that coverage is either exaggerated or flat out wrong. China has not cloned ASML's scanner. Copying that plasma source, part for part, tin droplet for tin droplet, would take years the country doesn't want to spend and might never fully catch. So the researchers at Tsinghua University did something much more interesting. They went after the light itself, using completely different physics. To understand what they built, forget tin droplets entirely. Picture instead a ring, a racetrack for electrons, called a storage ring, the kind of particle accelerator you normally find at a national physics laboratory. You take a beam of electrons, you accelerate them to nearly the speed of light, and you send them looping around the ring over and over. Now, normally, the electrons in that beam are spread out in long, loose clumps, about a centimeter long, spaced roughly 60 centimeters apart. Loose clumps like that give you ordinary synchrotron light, useful for science, but nowhere near powerful or focused enough to print chips at high volume. The trick that Tsinghua team is chasing is a way to squeeze those loose clumps into something extraordinary. Using a carefully tuned laser inside a device called an undulator, they nudge the electrons so that after one full trip around the ring, they snap into incredibly tight, evenly spaced microclumps, each one about a single micrometer long. When electrons are packed that tightly and that regularly, something remarkable happens. They stop radiating like a messy light bulb and start radiating like a laser. All their light waves line up, and because the electrons keep circling the ring, they keep doing it, continuously, in a steady state. That's the name of the whole idea. Steady-state microbunching, SSMB. Now compare that to ASML for a second, because the contrast is the entire point. ASML's source is basically a strobe light. It makes EUV in 50,000 separate violent little explosions per second, with all the tin debris and downtime that come with them. The SSMB approach doesn't explode anything. No tin, no droplets, none of that debris to sweep out of the chamber. Just a beam of electrons in a ring, gently coaxed into producing a smooth, continuous, laser-like river of extreme ultraviolet light. And on paper, the numbers it promises are staggering. The peer-reviewed research describes SSMB as a path to kilowatt-level average power in the EUV range. To put that in perspective, ASML's current production light sources put out a few hundred watts, and the company is spending the rest of this decade fighting just to reach 1,000 watts by around 2030. SSMB is aiming at that ballpark from a completely different starting line. And there's a reason raw power matters this much, a detail that rarely gets explained. EUV light is so fussy that you can't focus it with normal lenses. It gets absorbed by nearly everything, including ordinary glass and even air. So the entire optical path inside these machines is built from mirrors, and even the best mirror humanity can make loses roughly 30% of the light every single time the beam bounces. Professor Tang Chuanxiang, who leads the Tsinghua effort, has pointed out that the light can bounce around 11 times on its way to the wafer. Do that math. After 11 bounces at 30% loss each, only a sliver of your original light survives to reach the silicon, which means you have to start with an absurd amount of power just to end up with barely enough. That is the wall ASML's tin droplet strobe keeps slamming into, and a continuous laser-like source is one way to blow straight through it. Here's the part that should make you sit up. A single one of these accelerator rings wouldn't feed one machine. Because the electrons circle a big loop, you could place many lithography stations around the outside of that ring, like workbenches around a central sun, and feed all of them from the same source of light. One national-scale light source, powering an entire fabrication complex at once. In the Chinese press, this vision picked up a nickname that tells you everything about how it's being received there. They started calling it the lithographic cannon, and that flips the economics in a way that's easy to miss. ASML's model is one giant delicate light source bolted to one scanner, sold for hundreds of millions of dollars, one machine at a time. A storage ring rearranges that completely. You build the hard, expensive part once, the accelerator itself, and then you hang relatively simpler exposure stations off it, as many as the ring can feed. If that ever works at production scale, the single most expensive piece gets spread across a whole floor of machines instead of loaded onto every one of them. And ASML's entire pricing model starts to look fragile. Now, I want to be honest about where the credit belongs, because this is where a lot of coverage gets tribal and dumb. This is not some secret Chinese invention that appeared out of nowhere. The core idea of steady-state microbunching was dreamed up around 2010 by an American, one of the most respected accelerator physicists alive, Alexander Chow, together with his graduate student Daniel Ratner at Stanford. They published it, and then the theory mostly sat on paper for years because nobody had the right machine to test it on. What changed is that a young physicist named Jujie Deng, working on his doctorate at Tsinghua University, took Chow's idea and pushed the math much further. Chow personally connected the Tsinghua group with accelerator physicists in Germany, and together with Germany's National Metrology Institute, the PTB, and the Helmholtz Center in Berlin, they finally got access to a machine special enough to try it. Because this is the twist most of the coverage skips entirely. The experiment that proved this could actually work didn't happen in China at all. It happened in Berlin, on a German storage ring called the Metrology Light Source, the first ring in the world ever designed to run in the exact unusual mode that SSMB requires. In February of 2021, that international team published their result in Nature, one of the most rigorous journals in all of science. They had done it. They had taken a real electron beam and forced it to microbunch and radiate exactly the way the theory said it should. It was a proof of principle, the crucial step that takes an idea from 0 to 1. And it turned SSMB from a nice equation into something the whole semiconductor world suddenly had to take seriously. If you're getting something out of this breakdown, do me one favor and subscribe, because this channel goes deep on exactly these stories, the technologies that quietly decide who wins the next decade, long before they ever reach the mainstream news. All right, Back to why this one result keeps semiconductor strategists in the West awake at night. It comes down to what a monopoly actually is. ASML's power was never really about being better at making chips than everyone else. It was about owning the one road every chip maker had to travel. Every sanction, every export control, every choke point the United States and the Netherlands built over the last several years assumed that road was the only road that existed. Those controls were designed to guard one specific road, ASML's machine. They were never designed for the possibility that physics quietly offers a second road to the exact same light. If China, or anyone else, can generate 13.5 nanometer light from an electron ring instead of a tin plasma, then all those export controls are suddenly aimed at the wrong target. They're guarding one door while somebody quietly cuts a new one through the wall 100 meters away. That is what ASML feared most. Not a competitor who plays the same game slightly worse, but one that refuses to play the game at all. Now, before you get carried away, I promised you honesty, and here comes the cold water, because it genuinely matters. That 2021 experiment demonstrated the mechanism. It did not build a working chip factory. The gap between those two things is enormous, and anyone telling you the monopoly is already finished is selling something. In that proof of principle setup, the electron bunches carried a tiny fraction of the charge a real high-power source would need. Turning a laboratory demonstration into a machine that reliably prints millions of chips with almost zero defects is a completely different mountain to climb. And this is the sobering part for anyone rooting for a fast upset. Remember that ASML's own journey, from EUV being called impossible to a working production machine, took about 30 years. China is effectively starting that clock now, on the light source alone. And the light source is just one component of a machine with hundreds of thousands of them. Researchers at the European Chip Research Center, IMEC, point to the hardest part of all, what they call the yield gap. That's the brutal distance between making beautiful light in a lab and printing millions of chips where almost none come out defective. You can have the most powerful, cleanest EUV beam ever built and still fail completely if your mirrors are a nanometer out of alignment or your resist chemistry isn't perfect. That's the part money genuinely cannot shortcut. It takes time, repeated failure, and a decade of hard-won learning that can't be downloaded or stolen. There's also a reason this hasn't already happened, and it isn't that Western engineers were asleep. Building a storage ring is a massive undertaking. We're talking about a facility with a ring somewhere between 100 and 150 meters around, according to plans reported by the South China Morning Post, for a site in China's new Xiong'an district. That's a national infrastructure project, not a product you roll off an assembly line. And even the underlying physics still has open questions. Getting from the Berlin demonstration to a stable, kilowatt-class EUV cannon that runs 24 hours a day inside a working factory is years of hard work at absolute minimum, and it could still hit a wall nobody has found yet. But none of that lets ASML relax, and the reason is simple. China is not the only one who noticed. In the United States, a startup called X-Light is chasing a closely related idea, using a large particle accelerator and a free electron laser to generate EUV light and pipe it into existing scanners. Serious money and serious physicists on both sides of the Pacific have quietly reached the same conclusion at the same time. The tin droplet strobe light, as miraculous as it is, might not be the final answer, and the future of the most important light in the world might belong to particle accelerators instead. The moment that stops being a maybe and becomes a when. ASML's decades of accumulated advantage in tin plasma engineering stops being an unbreakable moat. Think about what a cheaper, higher power, cleaner light source would actually do to the economics. Right now, every wafer that comes out of a leading fab carries a slice of that $380 million machine cost baked into its price, plus all that maintenance downtime from the tin debris. The entire industry is organized around scarcity. A small number of these tools, all from one supplier, rationed out to the handful of companies that can afford them. Crack the light source open, and the effect goes far beyond helping one country. You threaten the scarcity itself, which is the exact thing that makes ASML worth $670 billion in the first place. Some analysts have started sketching a future where advanced chipmaking splits into two separate tracks, a Western one built around ASML's EUV, and a Chinese one built around accelerators and brute force workarounds. Whether or not that full split ever happens, the shift is that it's now even plausible. For 20 years, there was effectively one path to a cutting-edge chip. That is starting to change. And leverage is really the word that matters here. For years, the export controls worked partly because everyone involved believed they were airtight, that there was simply no way around ASML. The moment a credible alternative exists, even one that's a decade away from a working factory, that belief starts to crack. It changes how China negotiates. It changes how hard the West can squeeze without pushing rivals to build their own stack. And it changes how comfortable the world's chipmakers feel betting their entire futures on a single supplier in a single small country. Those controls leaned heavily on everyone's confidence that there was simply no way around ASML, and steady-state microbunching doesn't have to print a single chip to start eating away at that confidence. That is also why the money is moving the way it is. China has reportedly poured the equivalent of tens of billions of euros into building a domestic lithography ecosystem from the light source up, and the SSMB effort is one of the crown jewels of that push. There's even a second, noisier Chinese effort chasing EUV a different way again, using something called laser-induced discharge plasma, though that one is far less proven and wrapped in a lot more rumor. The point is the sheer scale of the ambition. That kind of spending is a bet on the next generation of lithography entirely. Michael Purvis, one of ASML's own lead technologists on EUV light sources, has spoken openly about how hard they're pushing their tin plasma design toward 1,000 watts and beyond, and that confidence is completely earned. But it is the confidence of the incumbent, the one company betting everything on the current approach staying on top. So let's come all the way back to where we started. One company, one town in the Netherlands, one impossibly hard to make part that the entire modern world runs on, and that an entire geopolitical strategy was built to protect. What that international team demonstrated in a Berlin laboratory does not break ASML's monopoly today, and it might not for a decade. But it proves something almost as dangerous to it. It proved the monopoly was never permanent. ASML's advantage always came down to controlling a single bottleneck, and a monopoly on a bottleneck only lasts as long as the bottleneck does. A light source, though, is the long game, a decade-scale bet on the machines of the future. And while everyone was staring at that future, China already did something the experts swore was flat-out impossible, using tools it supposedly wasn't allowed to have. And it did it years ago, inside a phone you can buy today. How a sanctioned company printed a cutting-edge 7-nanometer processor without a single EUV machine. The chip, ASML said, could not be made. That whole breakdown is on screen right now.